This is our second system, incorporating 2 pulleys and an incline, a stationary or free moving, and the incline. As the incline cut down the force to move it in half, and the pulley system is a 2-to-1, which cut it in half again, so in total it's a 4-to-1 mechanical advantage. As you pull it, it takes 4 times less force than initially take it to pull it straight up. This mechanical advantage is 4-to-1, so the effort I put in is 4 times less on my end, but I have to pull it for 4 times the distance as this travel vertically. As I pull this up 26 centimeters, I have to pull 104 centimeters of rope for it to travel 26 centimeters vertically.
So effort is the amount of force you exert into your system, and let's isolate the portion of our system by looking at the ramp. So a ramp helps you exert less force into a system. You just have to do it over a longer distance. When I place an object on the ramp helps me split the force of gravity into vectors. A vector down the incline path, and a vector up the y-coordinate, perpendicular to the incline path. And then you can find the f of g of on the incline path by using the angle, which we found. Our system had a rise of 26 centimeters, but a run on the hypotenuse of 52 centimeters. So we found an angle which would be 30. So when we multiplied the f of g with sine 30, mgx would be pulling half the amount of the regular fg if you were going up. So a physics concept is as the angle decreases or the slope becomes less steep, the fg sine theta decreases as well, which reduces the force needed to lift it up, but you need more distance to do it. The work would always be constant and equal to each other. So as you can see, when you work up, you're lifting the weight up. So this is the fg, and you're lifting it up 26 centimeters. But on a work on an incline, you split the fg in half, but you just have to travel twice as much. So it gives you a 2-to-1 mechanical advantage because you have to apply less force to lift it up. You just have to do it twice as long. However, that's an ideal mechanical advantage. The ideal mechanical advantage would be 2-to-1 with a theta of 30, because sine theta is 50. But a ramp is always going to have a lot of friction, so the actual mechanical advantage is going to be less than 2-to-1.
As Mon last discussed how the ramp works, so our system has pulleys, as we have 1 stationary pulleys and 1 free moving, and this just to pull it up to make sure it goes like that in our system, as we don't actually need it as a pulley. So this would be T, and this would be T, and this would be split into half, so it would be T over 2 and T over 2, and this would be the last string to T over 2, as we only pull T over 2 and the string get attached to the roof or the ceiling. And so this T would be whatever counteracting this part, and this would be FGX, which is 1.134 times 9.8 times sine of 30, which is 0.5. And so this T will also get split in half again towards the end, so it would be 1.134 times 0.5 times 9.8 divided by 2 would be the tension that we finally pull. So this would result in a quarter of the original tension if we was supposed to pull it down here. As we split half right here and split another half over here again. We pull 4 times 26 or 2 times the 52, which is 104. The mechanical advantage is 4-to-1. That's without friction and massless pulley, but our pulley have mass, and also there's friction along the ramp and friction along the pulleys. So our actual mechanical advantage would be less than 4-to-1. As for efficiency, the ideal efficiency would be our original scenario of workout, which is this block, 1.134 times 9.8, and for it to travel 26. Work in, which would be 4 times less. So it would include the incline and the distance we move. So it would be 1.134 times 9.8, sine of 30 over 2, as we got from here. And the total distance we're going to travel for it to pull and for it to move 26, or the height of 26. But now with and this would result in 1, which times 100 would be 100% efficiency. But in actual with friction, we have to account that workout would still be the same as 134 times 9.8 for it to travel 26, right? But now the force we have to put in to account for friction as force plus force of friction, because we we add force of friction to overcome the friction on the ramp and friction on the pulleys. We time this by 104, which is the total distance we travel. As the denominator would be bigger than the top because of force of friction, so this would be less than 1. And so time this by 100%, which would result in less than 100%.